Good day, and welcome to today's webcast, How to Achieve Compliance with the new 10 to the minus 16 BER Contour Spec in DDR4, sponsored by Keysight Technologies, formerly Agilent's Electronic Measurement Group. I'm Don Toot, and I cover analog and test issues for electronic design. Hey, a few words about your console before we begin. If you have any technical difficulties during today's session, first thing to try is function key F5 on your keyboard. That'll refresh your webcast console. If you need further assistance, you can click on the yellow help icon below the slides. To maximize the slide presentation window, press the small green button at the top right corner of the slide window. We welcome your questions during today's event. Type them into the question window on the side of your screen and hit submit. We'll answer as many as possible during the Q&A session that will follow the main presentation, but there's no need to wait. Feel free to send in your questions at any time. Today's session is being recorded. It will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. You may also download a PDF copy of the slides today by clicking the green folder icon in the toolbar beneath the slides. So let me introduce today's speakers. Colin Warwick is the high-speed digital product manager at Keysight EDA, where he is focused on multi-gigabit per second design and analysis tools. Prior to joining Keysight EDA, Colin was with the Royal Signals and Radar Establishment in Malvern, England, and Bell Labs in Homedale, New Jersey, and the MathWorks in Natick, Massachusetts. He earned bachelor, master's, and doctorate degrees in physics at Oxford and has published more than 50 technical articles and holds 13 patents. Fangyi Rao received his PhD in physics from Northwestern in 1997 for research in quantum theory of magnetism and transport. He joined Keysight EDA in 2006 as a senior development engineer, where he works on analog and RF simulation technology in ATS and RFDE. So let me turn things over to the first of our presenters. Colin, the floor is yours.
Thank you, Don. So as Don mentioned, the title today is we're going to talk about how to achieve compliance to the 10 to minus 16 BR Contour. That's a new spec in DDR4. I'm joined today by Fangyi Rao, who's going to do the Q&A, and also not shown this slide, Heidi Barnes, my colleague. Just a quick reminder that Keysight Technologies is the name. We were spun out of Agilent. The electronic measurement group of Agilent was spun out into Keysight Technologies, hence the new name you might not be familiar with, but hopefully you soon will. So before we dive into the BER contours, let's take a step back and look at some special considerations around DRAM. Now, most chip-to-chip interfaces have kind of gone serial. And the motivation for that is to eliminate the clock skew problems of parallel buses, other benefits as well. But DRAM has not gone this route, and the reason is that DRAM chips require a rather specialized process optimized for low leakage, and not the conflicting goal of a high-speed process. The ones and zeros in DRAM are stored on very small capacitors, around tens of femtofarads, and the difference in charge between a 1 and a 0 it's only about 100,000 electrons, so low leakage is absolutely crucial. And as you can see from the table, the DRAM process is optimized for low leakage, but not the conflicting goal of a high-speed logic process for SerDes. So another consideration is the clock skew problem isn't too bad for memory because the distances are usually fairly short. 5 inches is typical for a memory bus. So this clock skew problem isn't too severe, and we believe that parallel memories will be with us for some time, and they won't go series. There may be a few exceptions like hybrid memory cube, but the bulk, we believe, will stay parallel. So to tackle the DDR problem, let's look at the workflow tasks, the specifications, the methods and tools. As you can see on the top of this table, going from left to right, we're showing the tasks chronologically. The first task we consider is what we call design space exploration. Very early on in design, you want to sweep through various design parameters and find the sweet spot in the design space. The next step I'll consider is what we call prefabrication sign-off. This is just before you tape out your PCB or chip. You want to do a full compliance run on the simulated design in order to maximize the chance of the prototype coming back functional. And then the last step on here on the right-hand column is post-fabrication compliance of the hardware prototype as part of a lab test bench where you use your oscilloscope to actually measure the prototype. Just advance the slide here. During each of these tests, there are one or more specs you want to focus on, but before we look in detail on the main topic of this webcast, which is this new BER Contour Spec, which we talk about on the second and third rows of this table, let's first contrast this new spec with the traditional electrical and timing spec that we've had since the original DDR, and even before that. And indeed, these traditional electrical and timing specs carry forward to DDR4. We actually recommend you skip these during the design space exploration, and you only run these electrical timing specs because there are hundreds of them. Just run them once or twice towards the end of the design phase at sign-off on the release candidate. And when you do this with our tool set, you get the unique capability of Keysight Solutions is that you can use the exact same compliance tests with no ifs, ands, or buts on both the simulated waveforms in your release candidate and the physical prototype measured waveforms on the physical prototype in your test bench on your Infineon oscilloscope. So the idea of the electrical and timing compliance before we get into the BER as compared to the traditional method is you run a transient simulation on IBIS models or SPICE models of the controller, the memory, and the channel. You can collect waveforms just a few thousand bits to do the electrical and timing specs, so it's not too prohibitive in terms of simulation time. You can measure the setup and hold time and a few other critical figures from the waveforms. You can run this full compliance test to verify the final design and then compare the measured oscilloscope waveforms when the prototypes come back from fabrication. Unique capability of Keysight Solutions in this space is it solves the problem illustrated here. Your design, whether it's you're focused on the controller or the overall PCB system or the DRAM chip itself, they always begin in the virtual world of EDA schematic capture, layout, and simulation. So if you use other EDA companies, they might provide a script that generates a compliance report, and let's say it passes. And on the strength of that pass, you invest the time and the money to build a prototype. Then you get the prototype back from the fab and set it up in your lab as part of the test bench. You might capture the DQS bursts with your oscilloscope, and your oscilloscope vendor, if it's not Keysight, might provide an app that generates a compliance report. But now let's say this report says fail. What's happened? Is my physical prototype different from the simulation? Or is it that the EDA company's compliance test is different from the scope vendor's app? How do I correlate these two apps and get to the bottom of, is it my prototype or is it the vendor's software? So we've solved this problem with our solution for this electrical and timing space, leveraging our unique position as part of Keysight, which is one of the few companies that has both EDA tools and oscilloscopes. So you can design and simulate in ATS, use what we call a waveform bridge script to write the a file format that our scope compliance app understands. Get a pass on the compliance app using the scope app in its offline remote mode, running on a PC. And then when the physical prototype comes back, run it on a test bench, measure it with your Infineon oscilloscope with the same compliance app. And you know that because the apps are identical in both cases, if there's any problem, it must be between the design and the prototype. There's no question about whether the compliance app of the EDA vendor and the scope vendor is different because they're identical apps. They're running on the same software. Now, electrical and timing compliance specs are all very good, and in fact they're essential. But they have some problems in that with this short kind of waveform, it's very difficult to accurately account for bit-to-bit variation due to random jitter. In the simulation world, it'd be prohibitively expensive to do a simulation that runs enough of these waveform segments to build up a comprehensive picture of especially the random jitter, because the random jitter has typically something like a Gaussian profile. And as you know, to get to the outliers in a Gaussian profile, you need to run millions and millions of waveforms and integrate them together to find out where the outliers are. So this is challenging. It requires new thinking. And it's driven by the fact in DDR4, this is the first really generation of DDR where this has come in. And the reason is that the higher data rate means the unit interval is much smaller and the margins are much smaller. We can't just pad for RJ anymore. The VDQ is reduced to keep the power consumption down, and that gives you more amplitude noise. So the timing margin is eroded by the intersimple interference because the UI is smaller for a given channel impulse response, and the RJ is bigger compared to the unit interval as a ratio of the unit interval. So let's look at our workflow now in terms of these new specifications. We have a new BER Contour Spec in DDR4, and there are really two approaches to measure it. One is what we're talking a lot about today, is the Statistical I method. This is a method which we've borrowed from the SerDes space, as it's been around for a number of years. And we created a new product to do Statistical I specifically for DDR4 and beyond. We call it the DDR Bus Simulator. And we're going to contrast this with the more traditional way of getting BR contours called the dual Dirac extrapolation. You can apply dual Dirac to a conventional waveform. We don't recommend this method for design space exploration. We recommend that you use the Statistical I method to do your design space exploration. I'll explain why that is in a second. It's basically because the Statistical I is extremely fast. We recommend use this method for signing off your DDR contour because you can't run enough bits in simulation to get enough data to get an accurate dual Dirac extrapolation. Obviously you don't have that problem on the oscilloscope test bench because you're running in real time. The SPICE simulators typically will run 1 million times or 10 million times slower than real time, so it's very difficult to get enough bits to drive an accurate dual Dirac extrapolation. So we're recommending this new Statistical I method for the simulation world. So the idea of the I diagram is, of course, you account for many, many different waveforms and you overlay them to form an I diagram, and you get a visual representation of how much variance there is bit to bit and build up this probability density function. You see why this is important. In the older generation where we only have 800 megabits per second, the difference between the traces, 10 to the 3 bits and 10 to the 16 bits, it's pretty small. You have plenty of open eye. The spread of the rise times is pretty minimal. But when you go to 3.2 gigabits per second, you can see with a smaller unit interval, even with a 5-inch line, you're getting substantial encroachment of the ISI and the RJ here. So this motivates this new spec. So obviously simulating a waveform of 10 to the 16 bits is very impractical. And we want to get an accurate view of where this contour is because the traditional method used as kind of safety margin to guard against design uncertainty. With the very sloping walls of the bathtub curves that we'll see in the subsequent slides, that design margin would be huge. You'd have to give up a huge design margin to guard against this. The higher the data rate, the more the margin is underestimated using a small number of bits. It's because of effects like jitter amplification and so on, and the fact that the memory of the channel is a much longer in terms of the number of unit intervals. The RJ contributes to uncertainty because it's no longer negligible at these small unit intervals. And the uncertainty grows with data rate because the channel cutoff causes a non-Gaussian RJ, which is very hard to model with dual Dirac. So this is what happened in the previous generation. Instead of looking at the eye diagram, now I'm going to look at a section through the eye diagram we call this the bathtub curve, where we plot the bit error rate versus the decision point along the unit interval. As you can see, these curves are generated by dual Dirac extrapolation. The blue part of the line is directly measured data, I think down to about 10 to the 5 bits. The gray part is an extrapolation by dual Dirac. And you can see that the side wall of the bathtub is extremely steep. And so any kind of error in the dual Dirac is not so important. You can add a small amount of padding, and you'll get a very low error rate just by adding a small amount of padding shown here in this kind of yellow vertical lines. When we move to the faster data rates in DDR4, with these small unit intervals compared to the RJ, we now see that the bathtub wall is quite shallow. And so if you don't know accurately where this gray extrapolation is going, you have to pad quite a bit. These yellow vertical lines now are padded for the uncertainty in the dual Dirac approximation. We're trying to extrapolate from 10 to the minus 5 BR down to 10 to the minus 16. That's a huge 11 orders of magnitude extrapolation. So obviously there's inaccuracy in the dual Dirac, and we need to pad for those errors, and that leads to guard banding and a non-optimal design. We have a white paper on the dual Dirac method, and it's given this URL here. And I don't want to go in detail to dual Dirac, but I just want to point out there are assumptions in it, and these assumptions especially break down when the channel has a frequency roll-off, a frequency knee. So as I said, we created a brand new product, the DDR Bus Simulator, that uses a completely different approach. We use the Statistical I Approach, and it gives a 10 to the minus 6 contour much more accurately and much quicker than a dual Dirac extrapolation of a limited amount of simulated data. We use Statistical I. What Statistical I does is we probe the channel, the TX and the RX, using a very short SPICE simulation. It's just equal to the impulse response of the channel. And then instead of trying to apply a very long sequence of bits to figure out the bathtub curve or the BR contours, we actually take this impulse response and apply statistical techniques to the stochastic properties of the bit pattern, the statistical properties of the bit pattern. We don't use the bit pattern itself. So we don't have to run a very long, 10 to the 5, 10 to the 6, 10 to 7 bits through the impulse response. We can actually calculate the bathtub curves and the eye diagram, BR contours, directly from the impulse response and these stochastic properties of the bit pattern. So this really suggests a new methodology. In the past, people explored the design space using setup and hold time. Now we're suggesting you can actually have a new methodology where your design space exploration is BER-centric. You can actually compute the trace probability distribution. You can use an RX mask, which is introduced in the DDR4 spec as a new design goal. It includes both the deterministic and an allowance for the random jitter. You can decide where the BR contour is versus the mask. And it avoids guard banding around this dual Dirac uncertainty. You can directly compare the mask with the BR contour that's calculated by Statistical I. So this is our new recommended method for design space exploration and for sign-off of the BR Contour Spec. So this is the product. It looks like an ATS schematic. This is actually a whole byte lane with the 8 DQIs and also the DQSI for the whole byte lane. It uses a rigorous statistical calculation to calculate the BR probabilities down to an arbitrarily low BR and eliminates the design uncertainties due to dual Dirac extrapolation. You can check the contours against the DDR4 mask, and it also accounts for crosstalk between the signal lines automatically. So in the top level schematic, you just click Simulate with this controller, and you get these comprehensive results in seconds. This is on my laptop. This isn't a fancy workstation. This is just a normal kind of business laptop. And in 28 seconds, I get all this, the entire byte lane is solved. And you get comprehensive margins between the BR contours shown in red here and the mask, which is shown in pink. The bluish plots are the density plots. So this is kind of zooming in on the results here in a little bit more detail. We can see here we've got margins around the distance between the corners of the mask and the nearest part of this red BR contour. We have all the byte lane plotted in one simulation, as well as the strobe is plotted too. In the product, we have built-in models for DQ and DQS transmitters or drivers. On the controller side, people are adding now signal processing. Obviously, it's cost prohibitive to add this on the DRAM side, but on the controller side, certainly people are adding signal processing functions. So we have in our model a Deemphasis capability that's built right into the built-in model. We're accounting here for the asymmetry between the rise and falling edges. This obviously, the DQ is single-ended, so you get some asymmetry, which is kind of different from the traditional SerDes where you have a differential pair, and asymmetry is not that important. On single-ended drivers, that's certainly very important, so we account for that. We have a physical jitter model, and transitions in the stimulus are shifted by the TX jitter model. On the receive side, again, the DRAM receiver doesn't have any fancy signal processing, but the controllers sometimes do, and so we offer you the option of putting in a continuous time equalizer on your receiver model with poles and zeros. Now, you might not want to use the built-in models. You might have some models that are external to our built-in models, such as IBIS models or netlist-based models. That's fine. We can accommodate those too. And you can mix and match. You can use built-in models at one end and netlist on the other, or whatever you want to use. When you're using an external model, IBIS or netlist, you use our built-in models just as an ideal pattern generator, and that will drive the IBIS model or the netlist model, the input of the whether it's a driver or a receiver, we can drive the input with this kind of ideal pattern generator. So in our iProbe for this product, we have very comprehensive mask margin measurements. We measure between the corners of the mask to the nearest point on the BR contour that you specify. You can specify the mask either out of the spec, or if you have some custom specification, you can specify that. And we give it all the voltage and timing margin, which is the timing margin is these horizontal green arrows, and the voltage margin is the vertical green arrows. So you get 4 of those for each of each type for each iProbe, giving you a total of 8. Oh, that didn't advance for some reason. Good. Because this thing is so fast to generate this comprehensive data set in just seconds, this becomes now ideal for design space exploration. You don't have to run long SPICE simulations anymore. You can get the BR contours directly in just seconds. And so it's ideal for sweeping through the design space. So here I've got a batch simulation. And you get comprehensive data display. You can use these sliders to sweep through the data set. You can sweep through the different lines on the byte lane. You can sweep parameters in your schematic and see how the parameters affect things like the timing margins. Besides using the built-in design of experiments in ATS, some people like to use external design of experiments tools, so we let you export the results into a spreadsheet for use in external design of experiment tools if you prefer to use that kind of external tool. We have a batch export component. Now, often you want to model actual vendors' ICs, and you can download these. In our case, one of my examples uses a controller model, courtesy of Xilinx. You can download that from the URL shown here. Just click through their agreement, and you can download IBIS models. We have an example where the DRAM model comes from Micron. Again, courtesy of Micron, you can download from Micron's website. And the Xilinx model is obviously the controller side. So that covers the DDR Bus Simulator. Before we go into Q&A, I'd like to say that the next steps would be if you want to evaluate this. We're currently in early access or beta with this product, and we'll be releasing it next month. And the configuration you'll need to run this is the ADS core with the DDR compliance test bench for the timing and waveform measurements, and the DDR Bus Simulator for the BER Contour specs. And also register for our next webcast. Okay, so that's the presentation, and I'm asking Fang-Yi and Heidi to join us now for the questions, if Don wants to read out the questions.
All right, thank you. Now, a few of you out there in the audience have already submitted your questions. We'll jump right in a moment. If you'd like to submit a question now, type it into the question window on the side of your screen and hit submit. Now, while we're answering the questions, we'd like to ask all of you to complete the feedback form. That's located at the top of your console. You can also access the survey through the red icon on your widget bar. So let me start with a question in the middle, because eventually we'll get back to revisiting the question of when all of this will be available. There are several questioners who had variations on that question. But right now, do you calculate and display the margin if the BER contour has a dip due to ringback?
Yes. Column mentioned the margins at the four corners of the mask. In addition, we also measure the minimum voltage margin on the upper side and the lower side of the mask from the left to the right side. Those two voltage margin measurements will also be generated and saved to the result file. And so if you have a ringback, and then you will see the minimum voltage margin that is smaller than the margins at the corner.
Okay. What external DOE does the export support?
It primarily supports JUMP. JUMP is a popular DOE tool many designers use. So if the designer run a batch simulation or sweep simulation, ATS can automatically generate a Excel spreadsheet, extract all the results user specified to measure, and compile a spreadsheet file with on the left columns are the design variables, and on the right side of the table are all the measurement numbers, and that spreadsheet can be sent directly to the JUMP and to perform the design of experiments.
All right, how do you place the mask in the input eye diagram?
Yeah, that has to do with how the controller functions. So in DDR4, the controller are become fairly sophisticated. So it dynamically adjusts the timing skew between all the DQ lines and between DQ and DQS. As a result, the controller has a way to optimize the timing relation between DQs and between DQ and DQS. So so the result of it is controller is able to position the DQS in the center of the DQ eyes as long as the DQ eye have a big enough opening. So so to mimic that process, ATS when ATS position the RX mask into the DQI, it will calculate the optimum reference voltage, which is called Vsynth in the spec, and also calculate the optimum timing position, and when place the mask in the center of the DQI.
All right, how does the impulse response handle crosstalk when it's being measured to be processed further with statistical properties of the bit pattern?
Yeah. So in the bus simulator, every TX is a victim and a aggressor at the same time. And the way ATS handles it is, it will at the first step when it characterizes the channel impulse responses, it will turn on one transmitter and turn all the other transmitter off, and then measure the response of all the probe point to this particular TX, and then this process will repeat for every transmitter to collect information from all transmitter to all measure point, and with that information, ATS can calculate the eye probability at each eye probe by accounting for contributions signals from every transmitters, and that way the crosstalk is taken into account.
All right, getting back to the standard, is the BER requirement for DQ or for DQS as well?
It's only for DQ.
Okay. And a similar question, well, let me get this right. If the W2309 module is specifically for DDR4 simulation, is it, all right, I think that was an is strictly used for DDR4 simulation.
Yeah, the reason why we didn't call it the DDR4 Bus Simulator is we believe this is a multi-release product, so we think it's DDR4 and beyond. We think that LP DDR4 and DDR5 will have this spec. So it's really applicable for DDR4 and beyond, because DDR3 and below had no BR Contour Spec, so the methodology is not applicable for DDR3 and below.
I would like to add an additional comment. Although the BR mask is specified only in DDR4, but there are designers that actually apply this BR-centric methodology in DDR3 design.
Yeah, if you have your own internal specs, you could plug those in, certainly, yeah.
Yes.
But it's not a JEDEC spec, you're right. That's a good point, Bangy, thanks.
All right,
So
this is cool. The questions are pouring in. Except for iMask, does the DDR4 need to do setup and hold timing analysis?
For DQ, there's no.
Yeah, go ahead, Tony.
One at a time.
Yeah, for DQIs, there's no setup and hold. Yeah.
Okay.
In DDR4.
All right. is the read and write or write and read DQ requirement the same, or can you use the same mask for both? That is,
both for what? Can you repeat the question?
all right. The read and write DQ requirements, are they the same for read and write, and can you use the same mask?
The DDR4 spec only specify the I in the write operation, okay? Because the spec is only concerned with the memory side. On the controller side, when the write operation is performed, the designer usually have a similar mask requirement on the controller side, but that requirement is not defined in the spec. It should come from the designer and the chip vendor.
All right. Do you have options that let you look at timing for address nets and DQs?
Not at this point. Not. I would say, let me refine my answer. Is not in the bus simulator, because the simulator is focused on the DQI BR. For the timing between command address line and DQS, designer can use the traditional waveform-based analysis, generate the waveform, and then run the compliance test to analyze the timing.
Thank you. Can we, meaning the user, manually change the vertical or horizontal position of the mask?
No.
That's a simple answer. Usually the controller centers the eye around the mask first, and it's not usually necessary to do that. But we center it at the 0, 0 point on the eye diagram.
All right. A practical question: if you already have an ATS Transient license, is that sufficient to acquire these tools?
This is an add-on to ATS Transient. Is a requirement for the DDR Bus Simulator. This is a new separate package. The DDR Bus Simulator calls ATS Transient to characterize the channel, so it's a necessary but not sufficient to have ATS Transient. You need to have this new 2309 package.
All right. You may not care to answer a question about future availability, but there's still a question.
Sure.
Will Keysight be creating a hardware DDR4 interposer evaluation kit?
This is a scopes question. They already. I'm not in the scopes division, but my understanding is they already shipped the DDR4 interposer. It's called the N2114 and 2115 products. If you go to keysight.com and just type in the search box DDR interposer oscilloscope, you'll find the product page there.
Excellent. Does the mask account for variances in VREF on DG? Does it automatically center around VREF?
Yes. Yeah. When VREF is determined by the so-called we-send, which is at the location of the longest horizontal axis of the eye. Yeah. Actually, so that is related to an earlier question that whether user can manually shift the mask location. Shifting the mask location basically is equivalent to subtracting certain amount of the upper margin, then put it into the lower margin if you move the mask up and down. And similarly, if you move the mask left to right, that means you subtracting some of the timing margin on the left and then add it to the right. So that is a trivial practice.
Another mask question then. Can I use a custom mask that's larger than the spec because I know what my system margin is?
Yes. The mask width and height are parameters you can specify in the iProbe.
All right, we're down to, I think, the last questions, which are, when is 2015.1 available, and generally, how does one go about getting the DDR example project, DDR4 example project?
Yeah, right now the DDR Bus Simulator, as you say, is part of this 2015.01 release. It's in beta right now. The general availability is scheduled for December the 8th. The example project I use was developed by Heidi, and she put it into her recent seminar. I forgot to put the link to the seminar materials into the material, but we'll get that link out to you. It's from our recent What's New seminar materials, so we'll put that in the follow-up email. The only thing about the example project is you have to, because the Xilinx models are proprietary to Xilinx, we deleted the models from the example, and you have to go to the Xilinx website and click through their agreement to get the models which complete the example. So that's because that IP is proprietary to Xilinx.
All right, so we've run out of questions, so that concludes today's presentation. On behalf of Electronic Design, thank you all out there for joining the webcast today. You're invited to attend our next event in the Tutorials and Signal Integrity webcast series, PCB Materials, Simulations and Measurements for 32 gigabits per second, I should say, and that'll happen on January 22nd, so you'll have plenty of time to get ready. All right, thank you to all, and to all have a productive remainder of your day.